A very important theoretical and practical concern in magnetism is the force that causes a motor to spin, or more generally, force and torque on a current loop. So here is a loop, and hopefully you can see the perspective compared to a plane there. There's the XY plane, and there's the Z-axis shown. And this loop is rotated at angle phi with respect to that plane. And there's a magnetic field penetrating through, perpendicular to the plane. The dimensions of the loop are side A and B. And now we have current flowing around this loop. Doesn't matter how the current goes there. That's a small detail to run current into the loop. So the loop finds itself in a magnetic field. Now current will flow through there, and obviously surrounding, or this loop surrounds a region of magnetic field. Well, let's determine, it's not just, the B field is all over the place, so don't look at it just where it's shown, but it's everywhere in the surrounding space here. So what about the force of this segment here, the right segment, in this magnetic field? Well, use the right-hand rule. Put your fingers in the direction of the magnetic field, thumb in the direction of current, and you'll notice that the force over here is in the plus x direction. So it's to the right, say. Well, plus x direction, that's the right segment. The force on the left segment, how about down here? Do the same thing with your right hand, and you should get negative x direction. So there is the force on those segments. Now how about the near and far segment? Here's the near segment, there's the far segment. Current's flowing like this. Now this direction is not vertical, nor is it horizontal. The vertical part does nothing, no force. Horizontal part does. So think of the horizontal part. Put your thumb in that direction. Put your thumb in this direction while your fingers are like this, and you will notice that your palm is pointing outward, or negative y. So there's the force on the near segment, and likewise over on the far segment you get positive y for the same reasons. From symmetry, these near and far pieces cancel, and so we have that, well, symmetry on the right and left as well. The left is negative to the right. The far and the near segments are equal and opposite as well. So the total force is 0 on the entire loop. The loop does not shoot off this plane and take off up into the air or something. There's no net force. What about torque? The right and left, provide a twisting force of this loop. Kind of looking at it from this point of view, would be clockwise. But about the y-axis, a torque about the y-axis. Now, the near and far forces are on the same line, so they don't provide any torque. So no net torque from those two forces. So let's consider pivoting along the y-axis. Here's the y-axis. We're going to let it rotate or pivot along there. What's the torque? Well, the torque is provided by the moment arm on the right side, this moment arm times this force. So, and then down here for this one, it's the distance from the y-axis down to the inclined plane, and then the force intersects there. So from the halfway point here, the distance from here down to the plane. Okay, that looks like this length times the sine of this angle will give you that distance. That's going to be the moment arm for the torque. So torque is R cross F, and that's Fr sine of theta, or phi, I'm sorry. The force, the radius, sine of the angle between them. But from the discussion I just had, both of these contribute to the torque. And IAB, that's the length of the current wire, that's the A, and B is the magnetic field. And the radius is just this length B over 2 times the sine of the angle, which is this part. So if I want to show it to you from the origin here, you could think of it from here down to the inclined plane and then over. So this much, this quantity. B over 2 sine of phi. Probably said too much about that. Now torque, IB, AB sine of phi. Just rearranging it. Well, look at that. A times B. That's just the area of the loop. Therefore, we can summarize. The torque is IBA sine of phi. The current, the torque is proportional to the current, makes sense. Proportional to the B field makes sense. Now we don't have the lengths of the sides of the loop shown, but it's the area of the loop. So that's a really important and useful result. Now phi is the angle between the area vector and the B field. The area vector is perpendicular to the area. So this area vector and the direction of the B field is also phi. Now loops of current are very important in engineering and technology. We're going to give them some special significance here and define I times A, current times area, as the magnetic dipole moment. We'll call it mu. It's a vector. Now we just had that torque is IBA sine of phi for a current loop. Therefore, torque is mu B sine of phi. And thus, torque is mu cross B. And we had an analogy to this when we studied electric dipoles. And we had this electric dipole moment P, which was really Q times D. So, and then we analyzed the energy and had negative P dot E. In a like manner, we can say that the magnetic dipole energy is U sub B is minus mu dot B. So there's a close analogy there. Well, let's do an example. We have a coil with 30 turns. Here's a picture of a coil. I'll put that in there for reference. So you know that in my drawing, which doesn't quite look the same, it's really what it corresponds to. So we have a magnetic field of 1.2 Tesla. And here's this coil. Current is 5 amps. Magnetic dipole points straight out of the area. And we're going to determine the magnetic moment and the torque on the coil. The magnetic dipole moment is IA, but I'm also multiplying it by N. N is the number of turns. So this is current 5, area, pi r squared, times the number of turns. Every turn contributes. So it's 1.18 amp meters. Now the torque is mu cross B. So that's NIA cross B. But we've already solved NIA. It's the 1.18. So mu B, 1.18 times 1.2 is 1.42 Newton meters. So now keep in mind that the torque acts on all the current loops simultaneously. But we already took that into account here. So don't do it again. It's not like this mu corresponds to a single loop of this wire. It's all of them simultaneously. We multiplied it by 30 already. So that is the torque on such a current loop. Notice that the torque is there even when, well, especially when, in fact, this loop, the area of the loop, not the vector area, but just the regular area, is parallel to the magnetic field. No flux is going through the loop at the moment. That'll prove to be an important consideration. Okay, we'll finish up here with a brief discussion of solenoids, which are just many circular loops of wire stacked on top of each other. Well, it's just a coil that has spatial extent instead of all being confined to a very thin region. So there's a length along which it extends. Now, considering the direction of the current, notice the current flowing in like this. You can kind of follow the path of the current, determine the direction of the magnetic dipole moment, mu, and then the amount of torque acting on that coil, and then the direction of the torque. Well, to get the direction of the magnetic dipole moment, nice little trick. Grab your right hand by the scruff of the wrist and wrap your fingers around this coil. Grab the coil, actually, in the direction the current, wrapping your fingers in the direction the current flows. So you should have your fingers coming around here, and your thumb will point in the direction of the magnetic dipole moment. So there it is. That's the direction. Now it turns out that the direction of that dipole moment is such that it's trying to align itself with the external magnetic field. So there'll be a torque trying to twist the whole thing into alignment with the external B field. Now for a single loop of the wire, there's a bunch of them, the torque is IBA sine of phi. For a number of loops, it's just n times that, which is n mu b sine of phi. So we have our answer. The torque is n mu cross b. Very simple and very similar to the regular coil. And as far as direction is concerned, since this is trying to twist into alignment, the magnetic dipole is twisting into alignment with the magnetic field, then you can use your right hand rule and wrap your fingers in the direction of that motion. Your thumb will point in the direction of the torque, which is into the page. Your thumb points, or I should say, into the screen. So I could put an X here. In. That's the direction of the torque.